finally we get to the word problems that actually have a scenario behind them. Okay, so in this one, example 4, it says the radius of a circle is increasing. Find the rate at which the area is increasing. So my keywords that I see in there are area and circle. Okay, when I see area and circle, I know that I'm going to use the formula for the area of a circle. And the area formula for a circle, of course, is pi r squared. So that's how we get started with that one. That's our first step. So you just have to read through and look to see what criteria show you which formula that you're going to use. Now with this, we're going to take the derivative of these sides with respect to t. We're seeing how fast the area changes over time, seeing how fast the radius changes over time. So we're going to take the derivative with respect to t, just like we did our prior problems. So take this derivative with respect to t, and take this derivative with respect to t. Okay, the derivative of a would just be 1, and then you would say dA dt. And on this side, I would bring my power down, so that would be 2 pi r, and the derivative of r would be dr dt. Now in this green derivative formula, I see these values, dA dt, r, dr dt. And I called them values. I should have called them variables. I see these 3 unknowns. So what I need to do at this point is go back up to the problem, and they should be given to me. Now, when you see a variable like r, plain r, that's just the regular radius. When you see a derivative with a t, that's a rate. Okay, so any kind of derivative with a dt on it is the rate. So dA right here, what that actually means is the change in the area, the rate of the area. This dr dt here means the rate of the radius. So the d's, the derivative part, that is the rate of change. Okay, so when I look back at the problem, it says the radius is increasing at 2 feet per minute. Find the rate at which the area is increasing when the radius is 10. Well, what I see for that is radius is 10. It says the radius is increasing, that's a rate. It's increasing at a rate of 2 feet per minute. And it says find the rate when the area is increasing. Find the rate of the area. That's what we do not know. Now I want to point back out why r is 10. R is your regular radius, and it says radius is 10. That's how I knew that one. The other one says it's increasing at 2 feet per minute. That's a rate. That's how I knew that one. Now let's go back into our green derivative equation over here. I don't know dA dt, but I know that r is 10 and dr dt is 2. So this answer right here would just be 40 pi. And that's what we would get. Now technically, the area is measured in square feet. So it would be square feet per minute. But I'm looking for the 40 pi. Okay, so let's try another one of those. A spherical, okay, so that means sphere. I'm looking for a sphere in my formula list. A spherical balloon is expanding if the radius is increasing at a rate of 2 inches per minute. At what is the volume increasing? So my keywords there are volume and sphere. Okay, the formula for the volume of a sphere is 4/3 pi r cubed. Sorry, I needed to see what color we're using. There we go. So let's take the derivative with respect to t of both sides. Yeah, I think I'd rather write that separately. So let me clean it up just a bit. again, my formula is 4/3 pi r cubed because it said volume of a sphere. And what I'm going to do with it is take the derivative of both sides with respect to t. Okay, so when I take the derivative of v, that would give me 1, but then I would have a dv dt. Okay, when I take the derivative of 4/3 pi r cubed, I'm going to get 4 pi r squared. Then I have to take the derivative of r with respect to t. Now let me show you about your 4/3 just in case you had trouble. You had a 4/3 coefficient when you brought your power down. You brought the 3 down. So the 3's cancel, and that's how I got that whole number 4. When I go to the side, I have a dv dt, I have an r, and I have a dr dt. I need to label those before I can go any further. Remember, the dt's are rates. It says the balloon is expanding, the radius is increasing at a rate. So 2 is the rate of the radius. At what rate is the volume increasing? So that was the question. How much is the volume increasing when the radius is 5 inches? Okay, so let's plug those in. dv dt would equal 4 pi 5 squared and 2. R is 5, dr dt is 2. So dv dt would equal 4 pi 25 and 2 all multiplied together. So that would equal 200 pi. Now volume is measured in cubic units. So since volume is measured in cubic units, it would be inches cubed per minute. Now I'm focusing on the 200 pi, but inches cubed per minute would be your rate. Let me say that again. Inches cubed per minute would be your units for your rate.